Well, good morning. This is 11 o'clock on Tuesday, the 26th of September, 2017. Should be linear algebra class. However, I'm the only one in the classroom. So we will get started without anyone else here, I guess. All right, let me get my pen set up. Where we left off last time, I was going to make an announcement before we get started, but it won't do any good now because by the time you hear it, it'll be over with. But I was going to say that the volunteer fair, I believe is what they're calling it, sort of like activities fair or that type of thing, is going on. Lots of campus organizations and off-campus organizations are down in the faculty staff dining room until 12 o'clock. But we'll be in class until 12, but if you wanted to go, I was going to let you know. But since no one's here, it won't do a lot of good. All right, we were on page 54, chapter 2, section 2.2. We were doing matrix multiplication. We had just talked about that matrix multiplication is associative. It doesn't matter what order you do. And that's what this example is going to show. It said find the matrix product ABC by grouping first the factors A, B, and then multiplying by C, and then take the matrix A and multiply it by the product of B and C, and see if you get the same. So here's what we've got. Matrix A is a 2 by 2, 1, negative 2, 2, negative 1. Okay. Matrix B is a 2 by 3, 2, 0, 2, 3, negative 2, 1. Okay. That is a 0. It's sort of an ugly 0, but let me see if I can clean that up a little bit. Okay, not much better. And matrix C happens to be a 3 by 2. Negative 1, 0, 3, 1, and 2, 4. All right. Now what we're going to do is first multiply A by B. Can we? 2 by 2 by 2 by 3? Yes, you'll get a 2 by 3 result. So let's do that. 2 by 3 result. 1, 2, 3, 1, 2, 3. Okay? To get the first entry here, the 1, 1 entry, you multiply row 1 by column 1. That'll be 2 times plus a negative 6 would be a negative 4. Okay? 2, 1. 1, 2, first row by second column would be 0, 4. The 1, 3 would be first row by third column. 2 minus 2 is 0. Okay, 2, 1 would be second row by first column. 4, negative 3 would be 1. The 2, 1 entry would be second row 2, 2 entry, second row, second column, 0, 2. And the 2, 3 entry would be second row, third column, 4 minus 1 is 3. And we want to multiply that now by C, which is minus 1, 0, 3, 1, 2, 4. Okay? Can we do that? 2 by 3 by 3 by 2, that's going to give us a 2 by 2, so yes, we can. And the 1, 1 position here will be first row by first column. That'll be a 4 plus 12 is 16, so that's going to be a 16 there. The 1, 2 entry, first row by second column, 0, 4, 0, that's just going to be a 4. The 2, 1 entry, second row by first column, minus 1 plus 6 would be 5, plus 6 would be 11. The 2 entry, second row by second column, 0, 2, and 12 is 14. Okay. Well, I seem to have missed the first one. Okay. I seem to have missed several things here. Let me make sure I copied right. Oh, man. That messed up everything. Why didn't you say something? Of course, you weren't here to say anything. So 1, 0, 2. That messed up everything. Okay? Oh, boy. It's going to mess up this entry, that entry, which will mess up this entry and that entry. All right, let's try it again. The 1, 1 position here is going to be 1 minus 6 is minus 5. The rest of them should be okay. Second entry, the 2, 1 entry will be 2 minus 3 is minus 1. Okay? Now that'll mess up the whole thing. See why it does it, but let's see what happens. Okay. Make sure I copied this one right. I think I did. So it'll be a 5 plus 12 would be 17. So that's a 17. Oh, that's why it didn't mess up, because the first entry was a 0. Okay. And then the next one would be a 1 plus 6 is 7 plus 6 is 13. There. Got it right that time, because I copied it right that time. Okay. What we're going to do next is multiply A, which is 1, negative 2, 2, negative 1, by the product of B and C. Well, B's a 2 by 3 by 3 by 2. That's going to give us a 2 by 2 result. So let's multiply B by C. That gives us a minus 1, the 1, 1 entry, first row by first column, minus 1, 0, 4, so that's going to be a 3. The 1, 2 entry, first row by second column, 0, 0, 8. And then the 2, 1 position, second row by first column, is a negative 3, minus 6 is minus 9, plus 2 is minus 7. Okay? And then the 2, 2 entry, second row by second column, 0, minus 2, plus 4 would be a 2. Okay, multiply these two together and you get a 2 by 2. Okay, so 1, 1 entry here will be first row by first column. Be 3 plus 14 is 17. Okay, the 1, 2 entry, first row by second column, be 8 minus 4 is 4. So far, so good. The 2, 1 entry, second row by first column, will be 6 plus 7 is 13. So 3 out of 4 is fine. The 2, 2 entry, second row by second column, 16 minus 2 is 14. Got it? So that doesn't prove it, but it illustrates that matrix multiplication, as long as the matrices are sizes that you can multiply, is commutative. And we showed we got the same result both ways we grouped them. Okay? Now, next one that we have, let's erase all this. I would ask if you had any questions, but you're not here, so I can't. I can, but you're not here to answer. It's showing that 2 matrices that you can multiply, AB and BA, are not necessarily equal. In fact, most of the time they're not. Here's matrix A, simple 2 by 2, 1, 3, 2, negative 1. Matrix B, another 2 by 2 is 2, negative 1, 0, 2. Okay. Make sure I copied it right this time. I think so. Okay, first we're going to do A times B. Okay, the 2 by 2 by 2 by 2 is going to be a 2 by 2. 1, 2, 1, 2. All right. First row by first column, the 1, 1 entry. 2, 2, 1 entry. Second row's first row, second column is -1, 6 would be 5. The 2, 1 entries, second row, first column, 4. And 2, 2 entry, second row, second column, -2, -2 is -4. All right. Two, 5, 4, -4. Got it. Now let's do BA. This was AB. Okay, BA is also going to be a 2 by 2. Now this is going to take a little more dexterity here because we're doing the rows from B and the columns from A. Okay, so it's kind of backwards from what we have been doing. The 1, 1 entry is first row from B, first column from A. That would be a 2 -2 is 0. So far, wrong. I mean, they're not equal. Okay, first row, second column, first row of B, second column of A would be 6 plus 1 is 7. Okay, the 2, 1 entry, second row of B, first column of A, 0, 4. And the 2, 2 entry, second row of B times the second column of A, 0, -2. Okay, I hope I did it right. It's kind of backwards. 0, 7, 4, -2. Got it. Obviously, they are not the same. In other words, nowhere close to the same. Same size, well, that's because both of them were 2 by 2s. If the first one had been a 2 by 3 and the second one a 3 by 2, you could have multiplied them both ways, but the sizes wouldn't have been the same. The first would have been a 2 by 3 if you multiply AB, but if you did BA, you would have been at a 3, 3. So they couldn't possibly have been the same. So the only way you can get them even close is that multiply 2 square matrices to give you square matrices of the same size, but like here, they still don't commute. Okay. Now, but it says, do not conclude from example 4 that the matrix product A, B, and BA are never equal. Sometimes they are, and if they are, they're kind of a special kind of matrix. But it said, try this. So I'm going to clear this out, and let's try these two. A is 1, 2, 1, 1. And B is -2, 4, 2, -2. Okay. Hope I copied right. So let's first do AB. That will be a 2 by 2. That's 2 by 2 by 2 by 2. It's going to be a 2 by 2. Okay? And the first entry is the 1, 1 entry, first row of A, column of first column of B, -2 plus 4 would be a +2. The 1, 2 entry, first row of A, second column of B, 4 minus 4 is 0. 2, 1 entry, second row of A, first column of B, negative 2 plus 2 is 0. And the 2 entry second row of A, second column of B would be a 4 minus 2 is 2. Okay. Sorry. Now, just a couple of little observations here. We multiplied these two matrices together, but when I first looked at B, I wanted to balk a little bit because it's obvious you could factor 2 out of every element of B and still have a nice matrix with whole numbers, or integers anyway, and that would be fine. But if you did so, you would notice that those two matrices look a lot like each other, okay? If you factored out that 2, it would have been a minus 1, 2, 1, negative 1, which is really close to what A is, and there's a reason for that, and we'll get to it later, but then you see your product is going to be 2 times the square 2 by 2 identity matrix, okay? Well, you factored out 2 there, so not too surprising here, but let's try the other way, and let's do BA, okay? Again, it's going to be a 2 matrix, 2 by 2 matrix. We're going to take rows of A by columns of B, so the 1, 1 entries, first row by first column, that would be minus 2 plus 4 is a 2 again. The 2, 1 entry, the 1, 2 entry is going to be, about this time every day it seems like I clog up and I'm getting so I can hardly breathe. And I don't know why. I went back to my office between classes and got me a little snack just to have a little more energy, but that seems nothing to do with the breathing thing. My head's just closing in, it feels like. Say the 1, 2 entry, first row of B, second column of A, would be minus 4 plus 4 is 0. The 2, 1 entry, second row of B, first column of A, would be 2 minus 2 is 0. And the 2, 2 entry, second row of B, second column of A, would be 4 minus 2 is 2. Yes, they are the same. Okay? So you get the impression these may be special matrices to have that happen. Excuse me. Indeed they are. But we're not going to talk about how special they are yet. We'll get to it fairly soon. Another important quality of matrix algebra is that it does not have a general cancellation property for matrix multiplication. That is when, if you have matrix A multiplied by matrix C, and you happen to know that's the same as matrix B multiplied by matrix C, that you can't just divide out the C's and say, therefore, A is equal to B. It is not necessarily true. And that's what example 5 is going to demonstrate. And again, there will be some situations where you can do that, but not in general. The general situation you cannot. So let's go to example 5. Here we have matrix A is 1, 3, 0, 1, 3, 0, 1. Matrix B, 2, 4, 2, 3. Matrix C, 1, negative 2, negative 1, 2. All right. I'm so sorry. I feel like my whole head is closing in on me again. Now, what they want us to do here is, okay, we're going to look at AC and we're going to look at BC. Okay, here is AC. A times C is going to be a 2 by 2. 2 by 2 by 2 by 2 is a 2 by 2. Okay, so 1, 1 entries, first row of A times first column of C, that would be 1. Okay. I was going to try to finish this one. Let me pause this. All right, sorry about the delay. I just had to go to clear my head. I couldn't clear a lot. I'm so congested, but I drank water and took a swig of soda, something to, I'm not sure it's going to work, but I feel a little bit better now. I can talk a little more, at least for a moment. I think it's the cold air blowing in, but I don't know. So AC, we did the first one, first row times first column, 1, or did I? 1 minus, no, I didn't. I don't know what I was doing. I must have been looked at the wrong one. Okay. I guess I need to go. AC, 1, 1, first row, first column. 1 minus 3 would be a minus 2. Okay? First row, second column, 1, 2 entry would be minus 2 plus 6 is 4. Okay? The 2, 1 entry, second row, first column is 0, minus 1. And the second row, second column, 2, 2 entry is 0, 2. Okay? So AC is 2, 4, or negative 2, 4, negative 1, 2. Okay? Negative 2, 4, negative 1, 2. Got it. Let's do BC. Well, BC is 2 by 2 by 2 by 2 is also a 2 by 2. The 1, 1 entry is first row of B, first column of C. That would be 2 minus 4 is 2, minus 2. Okay. The 1, 2 entry, first row of B times second column of C is minus 4 plus 8 is 4. The 2, 1 entry is second row of B, first column of C. 2 minus 3 is minus 1. And the 2, 2 entry is second row of B times second column of C, which is minus 4 plus 6 is 2. Hey, look at that. Obviously, AC is equal to BC. But just as obvious, A is not equal to B. You can't cancel out the C's and say, oh, well, AC is equal to BC, therefore factor out a C and you get A is equal to B. No, you don't, because A is not equal to B. Okay? Nowhere close to being equal to B. So you see there is no cancellation in general when you have that. Now I thought we had already hit this. I've taught this course so many times I can't remember the order on it anymore. But I guess now it says you'll now look at a special type of square matrix, one that has ones on the main diagonal, zeros everywhere else. Okay? I'll put it here. This is called identity matrix of size n. Now, notice they're always square. Okay? Okay? So that'll be a 1, 0, 0, 0, dot, 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 0, 0, 1, 0, dot, 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 0, 0, 0, 1, dot, 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 0, dot, 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 down to 0, dot, 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 down to 0, dot, 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 down to 0, dot, dot, everywhere, dot, dot, except here it turns out being a 1. So you have 1s on the diagonal, 0s everywhere else. It's called the identity matrix. They have to be square. You can't have any rectangular identity matrix, only squares. They can be 2 by 2, 10 by 10, 18 by 18. Any size you have, they've got to be square. And that's why I call I sub n. They're n by n matrices, n rows, n columns, 1s on the diagonal, 0s everywhere else. And that's called the identity matrix of order n. All right, what are some properties of that identity matrix? This is going to be the top of page 56. Clogging up again, I'm sorry. If A is a matrix, okay, of size m by n, okay, then the following properties are true. Okay, first, A times I sub n is always equal to A. Okay? Now, I sub n, remember, is an identity matrix. It's n by n. So you can multiply an m by n by an n by n, and you get an m by n, and that one will be identically what you started with. Okay? The B part here. Sorry. 1b. Okay, no. 1, 2, or A, B, or however you want to say this. If you have the I m times A, that's also going to equal A. But you see, the identity matrix multiplied by the left has to be an m by m identity matrix because A is m by n, and an m by m times an m by n is going to be an m by n. So the sizes are right now, but notice those are not necessarily the same matrices. So I am a identity matrix of order m. Remember, identity matrices are always square. Times a matrix A m by n is going to be A m by n again. Okay. So let's do example 6. We'll clear this out of the way. All right. Yes. I'm so glad you're here. I get so sick of talking to myself. I'm not a very good listener.
I'm sorry.
No problem. Okay.
How everything going?
Actually going pretty well. I had to stop right in the middle of things a few minutes ago because my head was clogging up again. It's something about first 2 periods, I have no problems at all.
Are you always in this classroom every year?
Yeah.
Every year?
Yeah.
Around the same time?
Well, I don't always have 11 o'clock class. In fact, I very seldom do. But I have before. But on Mondays and Wednesdays, I have a class that goes until 11:10 because it's a calculus class, and I have lunch and come back for a second calculus class. And sometimes, either at the end of the first one or the beginning of the next one, the same type of thing happens. So I don't know how it is. But anyway, glad you're here. Jasmine's so far not here. She wasn't here yesterday either. I have her in Cal 3 on Mondays and Wednesdays, and she wasn't here. So she must be sick or out of town or something. All right, what we're doing here is we're on page 56, chapter 2, section 2.2, and we were just doing the theorem on properties of identity matrices. Okay, let me turn on. Second.
2.2?
2.2, yeah. And just had introduced the concept of an identity matrix. Are you familiar with it?
Identity matrix. I think I have seen it before.
Okay. There are matrices that are always square, cannot be rectangular, always square. Okay? And the diagonal diagonal elements are all ones. Everything on the diagonal is one, and everything not on the diagonal is a zero. Okay? And since they're always square, you don't need a 2 index. You don't have to say m by n. You just say n, okay, or m, or whatever the number is. And that means how many rows and columns it has. So I2 would be 1, 0, 0, 1. Okay? I3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? Diagonals are 1, everything else is 0. Okay? And the theorem at the top of page 56 in section 2.2 is if A is a matrix, now A doesn't have to be square, it can be any size, an m by n matrix. Okay? So if you multiply A and m by n by I, that I has to be an n, because m by n, n by n. You have to have the same thing. So it has to be I sub n. You're going to get A, which is m by n. Now, it's going to be the same matrix. Now if you multiply the I in front of the A, now this I has to be an m, because this is the m by n, this has to be m by m to multiply by m by n, and you still get an m by n, and A doesn't change at all there either. Okay? That's what we just did in the theorem. Example 6 is going to illustrate that. So here is the A part of example 6. 3, negative 2, 4, 0, negative 1, 1. Now, if we multiply that by an identity matrix, what size does that identity matrix have to be?
That's 3 by 2.
Second?
That's a 3 by 2.
This is a 3 by 2. This is our A. It's a 3 by 2. If we multiply that by identity matrix, what size identity matrix does that have to be?
Should it be the same thing?
No, it can't be the same thing, because if you try to multiply 3 by 3, 3 by 2 by 3 by 2, you can't. Because
oh, okay, I got you. That'll be a 3 by 2. Okay, 2 by 3.
Okay, except identity matrices are always square. You can't have a 2 by 3 identity matrix. So what size is that?
2 by 2.
2 by 2, I2. Okay, this has to be an I2, and how would the I2 look? Second?
Negative 6.
No, wait. No, I, the identity matrix. What's the characteristic of identity matrix?
Oh, 0.
Not 0.
Oh, my fault. 1.
1.
0.
0.
0.
0. 1. You got it. Okay, let's multiply those together. Okay, what size are you going to get as an answer? This, by the way, is a 2 by 2. That's what I2 stands for.
3 by 2.
It's going to be a 3 by 2. So let's put in 1, 2, 1, 2, 1, 2. 3 by 2. Okay? The 1, 1 entry is going to be first row of this one, first column of that. That's going to be
what you pointing at, the negative 2 or you pointing at 3?
no, 3.
All right, 3.
3.
Plus 0 equals
3. Okay. Well, so far we got the same thing. Okay. The 1, 2 entry is going to be first row here. Second column here, that's going to be
0, negative 2.
Okay, so far that's the same. Negative 2. Okay. This entry right here is what number?
Row 2.
1, 2, so we'll take, no, it's not 1, 2, it's,
I said row 2.
oh, row 2,
Yeah.
which column? No, it's row 2,
First column.
so it's a 2, 1 entry,
Yes, sir.
so it would be row 2 by, I see what you were saying, okay, and that would be
4, 0, 4.
4. Okay, so far so good. This entry here is going to be the what entry?
2 by 2.
2 entry. So that would be second row, second column. That would be
0, 0, 0.
Yep, so far same. And this entry down here is the
3 by 1.
3, 1 entry. So you'll take 3, third row here, first column here. That'll be a
Negative 1, 0, negative 1.
-1. All right, 5 out of 6 so far. Okay. How about that last one?
3 by
3,
3.
3, 2.
Yeah.
Okay. So third row, second column.
0, 1,
1. You got it. So you see, sure enough, if you multiply A by I, as long as I is the right size, you get A again. This and that are identically the same. Okay? Now, let's do another one. This time what we're going to multiply by is going to be just a column vector or column matrix, -2, 1, 4. And we're going to multiply this by an identity matrix. What size does that need to be?
That is a 3 by 1. And in the matrix, 2 by 2. No.
So you're right. This is, your answer, this is a 3 by 1.
Yeah.
You got that right. So what size identity matrix does that have to be to multiply by that? If you're multiplying on this side.
1 by 1.
Okay. 1 by 1 by 3 by 1, you can't multiply. Because these two have to be the same.
Okay. 1 by 3.
But identity matrices have to be
Square.
square.
So it's a 2 by 2.
Okay, but 2 by 2 won't multiply by 3 by 1.
Okay.
What size does it have to be? You've been all over it. The second digit here has
It's
to
3.
be.
It's supposed to be a 3.
Okay, and if that's a 3, what does this got to be?
1,
No, this has to be.
2.
Has to be
Square.
square. And if this is a 3, that's got to be a.
A 4.
No, that's not square. What by 3 is square? The second one is the number of columns.
Yeah.
If that's 3, how many rows have you got to have?
3.
3 by 3. So that has to be an I3. Okay?
Yeah.
Okay, now you tell me what the I3 looks like.
1,
1,
0,
0,
0, 0, 1, 0, 0, 0.
got it. Okay? Now, when I multiply those two together, this is a 3 by 3 by 3 by 1. What size am I going to get?
You're going to get a 3 by 1.
3 by 1. Okay, so boop, boop, boop. Okay? So that first entry is, what's the location of this one?
First row.
First column, 1, 1. So you do first row here by first column here, and you get,
-2, 0, 0.
so that's a -2. Okay? What's this next entry here? 2, 1. So you do second row here, first column here, and you get,
0, 1, 0.
which is
1.
1. And what's that last entry here?
3 by 1.
3, 1. So you do third row here, first column here,
0, 0, 4.
Yeah, you got the same thing. Okay? So again, the right size I times A is equal to A. You got it. Okay. Now, it almost seems like this next thing, changing subjects altogether. Okay? Okay, what we have here is a matrix A, and that matrix A has to be square. The other A's we've been dealing with weren't. This time the A's have to be square matrices. Okay? Now, matrix A. There we have it. What if we multiply A by A? We usually don't write the dot sign in there. I just did it for what size are you going to get? Remember we said A squared, so it's n by n. Multiply by n, you get n by n. Okay? Now, we call that A squared. Multiplying a matrix by itself. Okay? And if we multiply A by A by A, that's A cubed. Right. So we call A to the kth power A, dot, 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 until you get down to K A's, okay? Where you have K factors here, okay? For any positive number K, that's true. Now, A itself is just A, or A to the first power, right? Now, what do you think A to the 0th power would be? You got it. And because A is an n by n, this would be the identity matrix of size n. Okay? Which, okay, if you haven't picked up on it now, the identity matrix for a matrix acts just like 1 does for a number. Because 1 by 7 is 7. I by A is A. 7 by 1 is 7. A by A is still A. Okay? So, A to the 0th would be the identity matrix of that size n by n. Okay. Now, with that in mind, here are some other definitions. What if we have A to the jth power multiplied by A to the kth power? Do you want to hazard a guess what that could yield? A to the j plus k, not count k. Okay? And here's why. A to the j was A times A times A times A, j times, right? Just like we said here. A to the k was A times A times A, k times. Okay? If you multiply A times A times A, j times A times A times A, k times, you get a total of j plus k times. That's A to the j plus k. Right? Sorry. Just like keeping a base, multiplying, same base, different exponents, keep the base, add the exponents. We did that in real number system. It works here in matrices as well. Okay? Now, on the other hand, if you had A to the j raised to the kth power, what do you reckon that would be? You multiply the exponents. Okay?
I thought so, but I ain't thinking how.
Yeah. So here's what this would be. A to the j would be A times A to A, j times. And then another one would be A times A times A, j times. And however many you had, when you kept multiplying together up to k times, then you have j of these, j of these, j of these, j. So until you had j times k factors of that. Yeah. So you multiply. So when you're multiplying matrices, same matrix raised to different powers, add the powers. When you're raising a power to a power, multiply the powers. Just like we did with real numbers as well. Okay? Now, j and k are non-negative integers. Okay? We haven't gotten into, in real numbers, you can have 7 to the minus 3 power. That's fine. That's 1 over 7 cubed. We're not there on matrices. We're keeping positive powers, not negative powers. All right, so let's take one and do it. Okay. Here's a matrix A, and that's going to be 2, -1, 3, 0. Okay. Let's do A cubed, which would be 2, -1, 3, 0. Yuck. Times 2, -1, 3, 0. Times 2, -1, 3, 0. Okay? That's what A cubed means. Multiply it by itself 3 times. All right? Now, let's multiply the first two together. What size is that going to be? 2 by 2. Okay? That first entry is going to be? Okay, it's going to be the 1, 1 entry. Right? So you take the first row here by the first column there. That would be
4. -3.
Which would be?
Still add, right?
Yeah. 1. Okay. This entry here is going to be what?
First row, second column.
Okay, 1, 2 entries. So it's first row here by second column here, and that would be
-2, 0.
-2. Right? Okay. And this entry here is the
Second row, first column.
okay, second row here, first column there, that would be
6, 0.
6. Right? And the last entry is going to be the
Second column.
right.
Second row.
So that would be
3. -3.
-3, 0. Okay, so it'd be -3. Now I can't look at that and tell that's A squared. It doesn't look anything like A. Okay? But that's A squared. Multiply that by A again. And let's see what we get. What size will you get? 2 by 2. Okay. That first entry there is what entry?
Row 1, column
Okay, so we'll do row 1 by column 1, which would be
2. -6.
which is?
-4.
Okay, -4. Okay. Okay. Next entry is going to be what number?
1 by 2.
1, 2. So that'll be first row by second column.
-1.
Okay, -1. Okay. And the next entry is going to be the
2 by 1.
2, 1. So it'll be second row by first column. That would be
12. -9. 3.
3. Okay. And the last entry is going to be the
2 by 2.
and that would be second row by second column, which is
-6.
-6. -4, -1, 3, -6. Okay? Now, so what? Okay, here we define this. We see how to do it. There's no easy shortcut. You just do it.
That's it, right?
That's it. Okay? That's all she wrote. Okay? And then we go to something else. Okay? I'm sorry. Yeah, no. All right. Then it said in section 1.1, way back, you saw a system of linear equations must have exactly one solution, or infinitely many solutions, or no solutions. Okay? Now you can use matrix algebra to prove that. Okay? All right, here's theorem 2.5. Since you don't have a book, let me go on and clear this out of the way and write it all down here. For a system of linear equations, precisely one of the following is true. Precisely. Now, to me, that means one and only one. So I don't know if that's what, yeah, that's true. That is what they mean here. Okay? A system of linear equations, precisely one of the following is true. Number one, the system has exactly one solution. Exact, and only one. Okay? Number two, the system has infinitely many. Okay? And three, the system has no solution. Okay? One of those has to be true. Either it has exactly one solution, has infinitely many solutions, not just a few, not just 7, infinitely many, or it has absolutely no solutions. Okay? So it's basically all, which is infinitely many, nothing, which is no solution, or possibly just one and only one solution. Okay. Now, they go through a little proof there. I was not going to do anything with that. Okay?
Because that third was system, no solution.
It has no solutions. None at all. Okay? And we've kind of already seen that when we were doing our matrix row reductions and that kind of stuff. You either get a solution, you have an infinite number of solutions, or you get something that's never true. No solutions. Okay. That's that rabbit, and we're through with it for now. Okay? Now we jump to a completely new topic, and that's called the transpose of a matrix. Okay. Goodness gracious, it keeps going to that. I'm wanting it to go there. Okay. Goodness. All right. Brand new topic. Transpose of a matrix. Okay? Simply put, the transpose of a matrix is formed by writing its columns as its rows. Okay? That's it. You just basically exchange rows and columns. Okay? So here is a generic matrix A. I hate writing these things, they take so long. A11, A12, A13, dot, 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 all the way up to A1, M. No, they changed the N. Goodness gracious. Yeah, it's an N. I guess they've always done N. Okay, A1N. and then you have A21, A22, A23, dot, 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 up to A2N. And you have A31, A32, that's ugly, A33, all the way up to A3N. Ugly N. Goodness gracious. 3N. All right. Then you dot, dot, dot them down until you get A sub M1, A sub M2, dotting that down, A sub M3, dot, dot, dot. And then we do dot, dot, dots here, dot, dot, dots there, dot, dot, dots everywhere. And our last entry is the A sub M N entry. Okay. Goodness gracious. Almost dizzy. All right. Now, the symbol for a transpose is A superscript T. Usually it's a capital T. I think I've seen some books that call it a lowercase t, but I think usually it's capital T. Now, just as a reminder, A has M rows by N columns, okay? And if you're changing or exchanging rows and columns, that means the A transpose would have N rows by M columns, okay? Now, okay, and the transpose says we exchange the rows and columns. So what was a row here becomes the column here, okay? So that's going to be A11, then going down A12, A13, dot, 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 down to A1N, okay? And you also are exchanging the rows, columns for the rows. So the first row here is going to be the first column here. I've already got the A11 in place, A21, A31, dot, 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 up to AM1. Okay? And okay. You just keep doing that. So the second row here is the second column here. A21, A22, dot, 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 down to A2N. The second row down here was the second column up there. A12, A22. It doesn't matter which one you do next. I think I'll go across next. So the second row here is the second column there, A1 to A. Oops, I messed that one up. I put A2 twice. Sorry about that. A21 twice. So, this second column here becomes the second row here. A12, A22, A32, dot, 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 up to AM2. And this one down becomes a A33, down to A3N. And going across here, I come up to the last one there, and that's like Okay. This one. AM3. And these dot, 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 all the way down to AMN. Okay. Okay. That's the transpose of the matrix. Okay. Their size is transposed, the rows and columns transposed, everything transposes.
So that's all that's talking about? It's like just transforming everything?
It's not transform, transpose. The transpose of the matrix, right. Later, if we had time, I don't think we'll get there, we'll talk about linear transforms, and that's the only reason I say stay away from that word, because that's going to have a different meaning later.
Okay.
Now, before we do example 8, there's a little discovery on the side here, okay? And it's not a trivial discovery. It's pretty involved. So let's see if we can hit it. I think that may be all we have time for. But here we have a specific matrix A, a little old 2 by 2. I love it. Okay, 1, 2, 3, and 4. Okay? And B is 3, 5, 1, negative 1. Okay. I wrote them off of, no, 3, 5, negative 1. I think I said it right and wrote a 5 instead. I don't know where my brain is. Huh?
I said, yeah, you said negative 1.
Yeah, and I wrote negative 5. Okay. I wrote those two close too. Now it says to calculate a few things here. The first is AB transform. So the first thing you got to do is write down what AB is. So let's do AB. So let's multiply A by B, which is 3, 5, 1, minus 1. Okay? This will be AB. Okay? What size will it be? Okay, that first entry will be?
That'd be a 3 and a 2 is 5.
Yeah, 3 plus 2 is 5. Okay.
5, negative 2, which is a 3.
3. All right. I'm not going to stand up then. I'll just let you call them out to me. Okay.
Alright, 9, then 4, which is 13.
Okay.
Then 15, negative 4, which is a 11.
11. All right. So that's AB. Now what they want is AB transpose. So AB transpose would be what? It's also going to be a 2 by 2. Well, what will it be?
That'll be 5,
5,
13,
13,
3,
right? 3, 11, right? Okay. So that's AB transpose. All right. Now, next thing we're going to do is A transpose. And what is A transpose?
That would be 1, 3,
Right?
2,
Right?
4.
Got it. Okay? And we need to do B transpose.
That would be 3, 1, 5, negative 1.
Okay. All right. Next thing is going to be A transpose times B transpose. So A transpose times B transpose. That's going to be a 2 by 2. Okay, so you're going to multiply those two together. You do it. Tell me. 18. Okay?
1 times -3, that would be a -2.
-2. Okay?
And 6 plus 20, which is 26.
Okay?
And then 2 plus -4, which is -2.
Okay. All right. Now, doesn't look very familiar, does it? Well, let's try a different combination. Let's do B transpose, A transpose. Okay? Now, I was doing this before you came in. That is, this row by those columns. Can you do that?
Yeah. 3, 2,
Yes.
5.
5. Okay. And this next one is going to be the 1, 2. So again, this row by second column.
9, 4, 13.
13. Okay.
10.
10. Wait. I don't see how you got 10.
6.
Say,
6.
where'd you get 6? Okay. This is the 2 1s, so it's 2 1s. So that'll be
Okay, 5. -2. Which is +3.
okay. And
15.
right.
-4, which is a +9.
Uh-huh.
No, 15 plus -4.
Right.
Oh, 11.
Okay. And looky here. AB transpose is the same as B transpose A transpose. Wow. Okay? So a transpose switches columns and rows, but then when you multiply them, a transpose of a product is the product of the reverse product of the transposes, which is weird. Okay? So we've done the number 1. It says make a conjecture. I think I just did. It says select 2 other square matrices and check your conjecture. I'm going to say we're okay with it. Okay? All right. Now, we have just a couple of minutes, so let me clear the screen, and I think we can do example 8 now. Okay? Find the transpose of these matrices. This is A. Matrix A is 2, 8. Can you tell me what A transpose would be?
8, 2.
No? It sounds the same, but written differently.
It's going to be 2, 8.
2, 8 also, but written as a,
1 by 2.
yeah, that was a 2 by 1, this is 1 by 2. You're absolutely right. Okay? Okay, here's the B. Whoa. Here's, goodness gracious. It started doing weird things to me, so I started doing weird things back. Okay. Here's the B part. This gives us matrix B is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Very creative matrix there. Okay? We want to know what B transpose is. What would it be?
That would be 1, 4, 7, 2, 5, 8, 3, 6.
Okay, perfect. Okay, the C one here.
It's a C.
There is a C. Okay, and that will be capital C is equal to 1, 2, 0, 2, 1, 0, 0, 0, 1. Okay, what would be C transpose?
1, 2, 0, 2, 1, 0, 0, 0.
I just said that. Because these two are exactly the same. Right? Now, I'll just give you a little hint here. This is what we call a diagonal matrix. All of the elements on the diagonal are the same. Well, it doesn't really matter that, but the things opposite diagonal are exactly symmetric with each other. And when you do a transpose of that, you get the same. Okay? And there is a D here. I don't know where I'm going to write it. Let's see if I can squeeze it in the top here. Here's D up here. And here's capital D. They're being very egalitarian with this. 0, 1, 2, 4, 1, negative 1. 0, 1, 2, 4, 1, negative 1. Okay? Yeah. And what would be D transpose? First, what size will it be?
It would be a 2 by 3.
Yes, and read out the entries.
0.
Yep.
1.
Nope.
0, 2.
Right.
1.
Right.
1. 4. Negative 1.
Got it. Got it. Okay, we just ran out of time. So we'll start next time with theorem 2.6. Okay? I don't think there's anything here. So we'll start at 2.6 next time. And we almost finished 2.2. So homework exercises in 2.2 will be any of the odds 1 through 5, any of the odds 7 through 11, do number 13, any of the odds 15 through 19, do number 21, do 23, do 25, okay, do 27, even though we really didn't introduce it here, but do it, okay, and then do any of the odds 29 to 33, do 35, and you can do 37. Okay. And we'll hold off from there because we'll get those properties in just the next thing. So we'll stop there at 37. Good deal. All right. And we should finish 2.2 next time and move on to 2.3.